You know, finding the volumes for prisms really aren't that bad as long as we take it slowly and really think about geometrically what's going on. For example, if we start off with a rectangular prism, sort of looks like a box, right? Well, you can actually think about finding the volume by thinking that, well, the formula is just we take the length times the width times the height. Or another way of thinking about it is we sort of find the area of the base and we multiply that by the height. So either way of thinking about it will lead to the correct answer. What is the volume of this? Well, it's going to be 5 times 2, which is 10, times 3, which is 30. And so the answer is 30. And then what are my units? Well, they're centimeters, but now we've got volume. We've got length times width times height, so we have centimeters cubed. So the answer is 30 centimeters cubed. Okay, so that's not too bad. How about this one? Let's take a look at a very special rectangular prism, the cube. So the cube is a rectangular prism where all the sides have the same length. So let's find the volume of a cube with edge length equal to 5 centimeters. Well, how would you do that? Well, you could just think about the formula we just talked about, which reduces down to just side cubed, because it's length times width times height, but all those are the same as the side. And so here we see the volume of this cube, which you could sketch out here if you wanted to. 5, 5, 5. The volume would be 5 cubed, or 125. And what are the units? The units are centimeters, but it's volume, so cubed. So not a big deal at all, not a big deal at all. You know, if we take a look at cylinders that are a little bit more interesting, for example, take a look at this one. This is a cylinder that's no longer a right cylinder, but it has a little tilt to it. It kind of looks like the leaning Tower of Pisa. So maybe we should call this the leaning, I don't know, what do you want to call it? I'll just call it, I'll just say, look, here it is. There it is. There's a cylinder. It's the leaning cylinder of Pisa if you want, but if you don't like Italy, that's okay. All right, so the question is, what's the volume? Well, the volume we can actually find out even though it's sort of leaning. And we just use the exact same formula that we already know. It's the same concept. We find the area of the base and we multiply by the height. But now we're not going to multiply by this sort of funny height. We're going to multiply by the straight height right up there. And so we take the area of this and multiply by the height. You know the way that I think about this? Let me tell you how I think about this. Imagine that this was like a whole bunch of, like a stack of bologna. Okay? Imagine it's a stack of bologna and it was sort of tilted a little bit. If you were just to sort of take your hand and straighten it out, then you would make this thing completely straight, and then you would see that that height would be 10. So in fact, this sort of leaning thing is actually the same thing as a straight thing with that as its height. Philosophically, that's what's going on here. And so that's why this formula is going to hold. So how would we actually find the volume of this? It's just the area of the base times the straight up height. So the volume equals pi times r. So that's going to be 6 squared, which equals 36, times the height, which is 10. And so I see 360 pi. And what are my units? Well, they're centimeters, but it's volume, so it's centimeters cubed. Neat. All right, let's try another question, see if we can sort of put some of these ideas together with a slightly more exotic question. We want to find the volume of a cylinder with a base area of 25 pi inches squared and a height equal to the radius. Now, there are a lot of words here, and this sounds a little complicated. The first thing I would do is draw a picture. So let's draw a cylinder. Okay, so there's my cylinder. All right, I need to know the height. I need to know the radius. Let's see what I know. Well, I'm told that the base area is 25 pi inches squared. That's the area of the bottom circle. Let's take a look at a top view. It looks like a circle, has a certain radius, and we're told that the area of that circle, because that's what the base is equal to 25 pi. And we know that the area of a circle is pi r squared, so this is going to be r squared pi. And if we simplify that, I see that 25 equals r squared. Well, I can now figure out what the radius is. What's the radius? Well, mathematically, if you were to solve this, there are two answers. The radius would be plus or minus 5. But of course, radius is representing a length, and so I know immediately that in this context, r, is this going to be 5? So the radius is 5. So we've just learned that our radius is 5. That's great news. What's my height? Well, the height is equal to the radius. Oh, great. Well, I just found the radius. So this height is also going to be 5. Now, you can see that my picture is not drawn to scale, but that's completely okay. The picture was there as a crutch to allow me to sort of understand the question. If I want to draw an accurate picture, I got to squash this down almost like a tuna fish can. All right, but anyway, we can still find the volume, because the volume is going to be what? It's going to be pi r squared h. That's going to be pi times r squared, that's 5 squared, times h, which is another 5. That's actually 5 cubed, or 125. And so the volume is 125 pi. And what are my units? My units are now inches, but they're inches cubed because I'm talking about volume, 3 dimensions. So you can see here, it was a little tricky question because the information was hidden. We had to first of all think and find the radius. Once we found the radius, using the fact that we knew the area of the base, we were home free. One of the themes we've seen a lot so far together is what happens when we take an object, a solid or any kind of figure, and dilate it by a certain scale factor and see how it impacts the area. And now let's see how it impacts volume. So let's take a look at this cylinder, and I want to compute the volume of it as is, and then I want us to compare that to the volume of the cylinder we'd have if I took this length and actually cut them each in half. So multiply each of these lengths by half. So we're going to sort of shrink the whole thing down, and let's see what the impact is on the volume. So first, let's find the volume as it stands. That's pretty easy, because what do I see? I see it's going to be pi r squared h. And so I've got pi times r squared. That's going to be 64 times h, which is 20. And so what I see here is 1,280 pi. Okay, so, and what are the units, by the way? The units are centimeters cubed. But I want us to focus on this number. All right, now, let's see what happens when we cut each of these lengths in half. So I make this a 4, I make this a 10. And now, let's compute the volume of this smaller cylinder. Okay, well actually I'm going to do it out and write it exactly as we would if we were dividing these things by 2. So check this out. So it's going to be pi times r squared. That's going to be, I'm going to write this out, that's going to be 8 over 2 squared, right? That's the half of 8 squared, times the height, which is 20 over 2, half of 20, and that's the answer. But if we just now simplify this, what we see here is pi times 8 squared, which is 64 over 2 squared, which is 4, times 20 times 2. Looks very familiar to what we've already seen, except for those denominators. And what does that equal? Well, the 4 on the bottom multiplied by the 2 on the bottom gives me an 8 on the bottom times, well, what we had left over. So 1,280 pi centimeters cubed. Now, you can actually work out that number. That number, if you care, is actually 160 pi. But that's not the point. The point is to look at this number right here. How does it compare to this? Well, this number is 1/8 of the original number. 1/8. Now, where did that come from? Well, we took each length and we actually multiplied it by a half. But when you're finding volume, it's units cubed. So it's actually a half times a half times a half. And what's a half times a half times a half? It's an eighth. And that's what we're seeing here. So the impact that we have on volume when we shrink the lengths is that we have a shrinkage in the volume, but not by one factor of that length factor ratio, but that thing cubed. In this case, a half times a half times a half. And so again, we can see how volume and before surface area is impacted by dilation.